We will wait a few minutes.
Okay, actually, I just want to know some things.
Yeah, sure, you can ask.
Yeah, actually, after week
Your internet is
one
having some problem, I guess. I'm not able to properly hear.
assignment was there, and after week two, another
Actually,
assignment is
your
there.
voice
So
is
I just
Can you ask again? Your voice was breaking. I'm not able to properly.
hello,
Hello.
hello.
Now you can speak.
Okay, okay, okay.
Hmm.
Okay, now is it okay? Now is it okay? Are based on week one lecture or week two lecture like this?
Huh. Can you ask again? Actually, I didn't hear whatever you asked previously.
Actually, in your assignment after week one lecture,
Huh.
we have to submit assignment.
Hello, Shalmali. Your voice is breaking. Can you ask in comment section? Hello, your voice is breaking too much. I'm not getting anything. Hello, hello. Can you please ask in the comment section or chat session? Am I audible, right? Hello. Okay, I will share the slides now. Is the slides visible? So good evening all. Welcome to week 2 tutorial section of the course Pericyclic Reactions and Organic Photochemistry by Professor S. Shangaraman from IIT Madras. Myself Anisha Suresh, PMRF TF for this course from IIT Bombay. So, okay, Shalmali, you can ask. We will start after that. Actually, your voice was breaking too much.
Yeah, yeah. Actually, now I am I audible?
Yeah, you are audible.
Actually, I just want to know that assignment one is based on only your lecture one, na? I mean week one lecture,
Yeah,
and assignment two is based on only week two lectures.
yeah, it
Okay,
should be.
and then I Okay, actually, I am facing one problem. Assignment one is almost over,
Yeah,
but assignment two, I am facing some problem to solve the questions. Actually, in your lecture, the mechanism is not showing. That's why sometimes I face problem to do the mechanism. In order to get the product, first of all, we have to do the mechanism now.
yeah, yeah,
So
yeah.
this is the main problem. So if you show some mechanism of the slide, the reactions that have been shown in the slide, then it will be very helpful for me.
Okay, for cycloadditions, you need mechanism.
In assignment one, I have solved the problems, but in assignment two, I'm facing problem. I mean, I it yeah, it takes a longer time, but I can't
Okay, okay,
do the mechanism.
okay. Uh,
And another question is that after submitting the assignments
hmm.
before the examination, actually I will for the exam. So before the examination, can we get the solved answers? Because after
Within
submitting the
one week
assignment,
or
we are
something,
not
you will
sure.
get the answer. Within 1 week or something,
Actually,
you
what?
will
Actually,
get. Hello.
your voice is breaking. I am not getting.
Okay.
So if you write in the chat box, then only
Sure.
I can read it.
Okay. Once you will upload the answers now, after that within a week or so they will send an announcement regarding release of the solutions. Okay, we will try to solve the mechanism. Like actually for this Diels-Alder reactions or this pericyclic reactions, so much mechanism sort of things are not there. Just we need to follow the method only,
Okay. Then that will
and
be
then
okay.
we have to
Perfect,
solve
fine.
it. Okay. Now we will go to today's lecture.
Mhm. Actually,
Again, your voice is
in
breaking. I don't know, problem with my internet or something. One
assignment
second.
two, I think it is
My problem might be.
yeah, it problem.
Hello, now is it audible? Okay, we will try to solve. Actually, from assignments directly, I cannot solve many questions. Actually, from direct assignments, I cannot solve many questions. So I will be solving some model questions which will be helpful for solving your assignments. Okay.
Okay, sure.
Mm. So I will share the slides now. So last week there was a doubt regarding one electrocyclic ring opening which was asked in CSIR net or so. So this was that question, right? Someone, I think someone from IIT Delhi, I don't remember his name. He was asking this question. So here maybe we can explain it based on 4n plus 2 system. Like this is a cyclopropane, and it will open to give vinyl carbocation. Cyclopropyl carbocation to uh, ring opening product. That is a actual mechanism that will be taking place here. So it is like two electron system. Two electron system will come under 4n plus 2, where n equal to 0. Okay, so 4n plus 2 delta, it will be 4n plus 2 delta, it will be disrotatory, right? According to Woodward Hoffman rules. So here we can expect like this will open, and bromide will leave, and we will be getting this product, and the mode of ring opening will be disrotatory. So the right answer will be B is formed as a major product via conrotatory ring opening. But here the concern was in one another question, where here similar question only, but here the position of chlorine and bromine is different. Here previously, see here the bromine was above the plane or endo, and chlorine was exo, and here it is exact opposite. Chlorine is above and bromine is below. So here the chlorine is removing and bromine is remaining as such, and we are getting the um, final product. So here what is the actual mechanism that is taking place means, so here you see this will be the bond that is getting broken, right? And it will be following this rotatory mode of opening. So it will be opening in this direction, like these two bonds will be coming in this direction. So this will open in this fashion. 4. So these two bonds will be coming like this, and the anti-bonding orbital of chlorine will be in this facing this side. So this electron will be given to the antibonding orbital of chlorine, making this bond more labile. So chlorine will be leaving, and we will be getting this carbocation. Then water will be attacking, and we are getting the final product. So whichever bond or whichever halogen is coming anti-periplanar to these bonds that are breaking, that will be leaving, and we will be getting the final product based on that. And according to electrocyclic reaction point of view, like it is a 4n plus 2 system, where that is a 2 electron system, and it will follow this rotatory mode of opening under thermal conditions. Okay, and these salts AgClO4 or AgOH, it is not having any effect on that. It is just making the halogen more labile, as you can see here. Here we can explain like bromine is a good leaving group, but actually it is coming anti-periplanar to that of the bonds that are opening. Because of that, electron density will be going to the antibonding orbital of the halogen, and it is leaving, right? Is it clear? These bonds will be opening in this rotatory fashion. So the antibonding orbital of bromine will come in this direction, and hence this will give electron density to the antibonding orbital and make the bromine more labile. Clear, right? This was a confusion from last week someone was asking. Now coming to, so this also is an explanation of that. Whichever group is coming endo to that of the bond that is breaking, it will be living. Here endo chlorine is coming, so chlorine will get removed and we are getting this product. And in this case bromine is coming endo to that of this bonds, so bromine will be living and we are getting this as a final product. Clear na? Just remember it is an electrocyclic ring opening of a two electron system. So under thermal condition it will follow disrotation, and photochemical condition it will follow conrotation. And another point is groups that are endo will be living groups. And this was another question. They were facing a doubt. Methanolysis of bicyclic dibromide with methanol in the presence of AgClO4 gives trans product 53. So this is also similar to electron system, that is this cyclopropane. It will generate cyclopropyl carbocation after removal of one bromine. So it is a two electron system, and it will follow disrotation as it is thermal condition. So it will open up, remove removing one bromine, and we will be getting 1 2 3 4 5 6 7 8 4 5 6 7 8. One second, I will draw it again. 2 3 4 5 6 7 8. So here a positive charge will be generating, here bromine will be there, and here a double bond will be generating. So why this trans product is forming, they are asking. So when we are drawing the stereochemistry, so that time this methanol will be coming from the least hindered side. So from that when the trans product is forming, that time only this least hindered attack will be taking place. That is why we are getting this trans product. Okay. So this silver ion, it will coordinate with the bromide ions, facilitating their departure as silver bromide and generate a highly reactive carbocation intermediate. So first here a carbocation intermediate will be forming, and this carbocation is relatively stable due to the cyclic structure, allowing for the nucleophilic attack by methanol from the less hindered side, leading to the trans product 53. So methanol will be attacking from the less hindered side. So maybe before opening we can explain. Before opening we cannot explain properly because So this opening will be taking place in disrotation fashion. So that is why this bromine will be leaving, because its antibonding orbital will be coming uh, parallel to that of this bond whichever is breaking, lobes of the bond whichever is breaking. So electron density will be given to that, and hence the antibonding orbital will get filled and that bond will be labile. So that bromine will leave, and then it will generate a stereochemistry such that the methanol can attack from the less hindered side. So we are getting the trans product. The reaction is stereoselective because the trans isomer is predominantly formed due to preferred backside attack on the carbocation. Okay. I don't know if that person joined today. Someone from last week asked these two questions. Now some previous week one assignment questions we can discuss. So here what will be the answer? This is the starting material. They are asking what will be the product that is getting formed here. So this is what sort of system? 4n, 4n plus 2. Which one?
Foreign.
Yeah.
Foreign.
It is a 4n system. 4 electron system. 4 electron system. So it is given 130 degrees Celsius means thermal condition. So 4n under thermal condition. What mode of ring opening will take place?
Conrotation.
Yeah. Conrotation will be taking place. So conrotation means like the arrows will be moving in the same direction like this. So from above it will be going outside. Here from above the CO2 Me will be going inside. So if we will draw, it will be like this: CO2 Me, CO2 Me. Both are moving in the same direction. Clear? So this will be the final product that is getting formed. So we have to be very much clear about the Woodward-Hoffmann rules. Then we can easily solve such questions. So see, like this only we have to mention the answer. Foreign system, conrotatory. Because of that we are getting this product. This is the solution whichever I got. Okay. No need of so much explanations. Now coming to another question. So this is the question. So what sort of electronic system is this? 4n or 4n plus 2?
4n plus 2.
It is a 4n plus 2 system, and under photochemical condition it is,
Conrotatory.
yeah. So 4n delta is conrotatory, 4n plus 2 delta is disrotatory, also 4n h nu is disrotatory, 4n plus 2 h nu is conrotatory. So here conrotation will be taking place. So this both will move in the same direction. So this methyl will be going outside of the double bond, and this methyl will be going to inside of the double bond. So if we are drawing cyclohexatriene, means hexatriene, it will be coming like this: Me, Me, PH, PH. So 4n plus 2 H nu conrotation, and this is the final product. Clear? This is all you have to mention. Now coming to another question. Sorry. Just 1 second. Give me a second. Sorry, I pasted the wrong question. Hmm. Just sharing the slides again. So this is the question. So here we are having this as the starting material. This as the starting material. It is heated and then treated with this uh, alkyne with substituted esters. So we are first ring opening will be taking place, and then a Diels-Alder reaction will be taking place. So they are asking to give the stereochemistry of the intermediate and the product. So this is what sort of a system? 4n or 4n plus 2?
4N.
Yeah, it is a 4n system. So under heat, it will follow
Conrotatory path.
it will follow conrotatory path. So after opening, it will be like this phenyl will be going outside of the alkene, and this phenyl will be going to inside of the alkene. So we will be getting like this will go outside, this will go inside. This will be the product that is formed. Okay, now this is an diene sort of system now, and this is the dienophile. So it will undergo a Diels-Alder reaction, and it will be giving the final product. So what will be the stereochemistry of the, if Diels-Alder reaction is going on? So here you can see this is sort of an E alkene, and this is sort of an Z alkene. So Stereochemistry of both the phenyls are like different, so it will be coming different in the product also, right? This is the diene, this is the diene, and this is the dienophile. It will react and we will be getting CO2Me, CO2Me, and these both two phenyl groups, if one is above the plane, the other one will come below the plane, like this. Okay, if this will come above the plane, this should be below the plane. So we have to write like this. This is above the plane, this is below the plane. Clear?
Yes.
Okay. Now coming to another question. What is the stereochemistry of the product? So here, even though it is a 4n plus 2 system, we are considering this part alone. As here you can see there is a 4-membered ring and a 5-membered ring fused together as a product. So this system is taking part in the reaction. So 4n H nu will be what we should consider. Okay. So but it will follow 4n system. Under photochemical condition, it should follow conrotation or disrotation.
Disrotation.
Yeah, it will follow disrotation. So if this group is coming like above the plane, the hydrogen will also come above the plane. Both will be moving in the opposite directions. So this which is outside, when it will come above the plane, this hydrogen which is outside should also come above the plane. So this will be the final product. Okay. Clear?
Yes.
Okay. So now coming to this question. Considering that the conversion of divar benzene to benzene is exothermic by 71 kilocalorie per mole, its kinetic stability is quite high. It has a half-life of 2 days at 25 degrees Celsius and the enthalpy of activation for the conversion is 23 kilocalorie per mole. Explain why divar benzene is unexpectedly stable under thermal condition, whereas it readily converts to benzene under photochemical condition. So this is the major part that you have to consider. Just divar benzene, that is this one, it is unexpectedly stable under thermal condition, but it will readily convert it to benzene under photochemical condition. So what could be the reason?
Actually, in thermal condition, mm, the if the in thermal condition,
Hmm.
it is a 4 pi electron system. So under thermal condition, it will follow the conrotatory path.
Hmm.
But in that case, the product is non-existent because the both hydrogens will be in transposition in benzene ring,
Yeah.
which is geometrically forbidden structure.
Okay.
But under photochemical condition, this problem will not arise.
Yeah. So that is the actual reason. So as you can see here, when we will follow thermal condition, so it is a foreign system. When we will consider this side, it is a foreign system and it should follow conrotation. So conrotation means If we move, one of the hydrogen will be coming in trans position like this. So this is geometrically forbidden case. That is why benzene under thermal condition will be highly stable and it will not get converted into benzene. But in case of photochemical condition, so if we are having benzene, so under photochemical condition, it will follow disrotation. Okay. So under disrotation, when it will move in this direction, both the hydrogens will be moving in this direction. So it will be coming outside. Both the hydrogens will be coming outside, which is geometrically allowed, giving benzene as the final product. Okay. So the product structure is not geometrically favorable because the proton is trans to the double bond in the phenyl ring. So the conrotatory process is allowed by the Woodward-Hoffmann rule, but it is geometrically forbidden. That is why benzene is unexpectedly stable at thermal condition. Clear, right?
Yes.
Now coming to this question, this also someone was asking last time. So explain why 1,2,4 tri-tert-butyl benzene readily photoisomerizes to the corresponding divar benzene. Other benzene derivatives such as toluene, xylene, mesitylene, etc. do not undergo this reaction. So under photochemical condition, this 1,2,4 tri-tert-butyl benzene, it is converting to this divar benzene. What might be the reason?
Actually, in the planar benzene structure, the three tertiary butyl groups provide considerable steric strain.
Yeah.
As a result, it will undergo non-planar dual-benzene structure under photochemical condition to release the steric hindrance.
Yes, you are right. So this is the thing. In case of benzene, it is a planar structure. So all the tertiary butyl groups will be like when we will consider this 1,2 positions, the tertiary butyl groups are having considerable steric hindrance. So once it will get converted into divar benzene, so there is uh, a release from that steric strain as the tertiary butyl groups are getting far apart in the space. So 1,2,4 tri-tertiary butyl benzene is sterically crowded molecule due to presence of two tertiary butyl group at the 1,2 position in the phenyl ring. So it readily undergoes this rotatory ring closing to give corresponding divar benzene. In divar form, 1,2 position tertiary butyl groups are far from each other. So the release of the steric strain is the actual reason for formation of this divar benzene in this case. Clear now? So some of the questions from the previous assignments I have covered here. Now we will be moving to few questions from this week. Before that, we will just have a brief review about this week contents. So coming to cycloaddition reaction. So in cycloaddition reactions, it will result in the formation of a new ring and it is designated as A plus B, like 4 plus 2, 2 plus 2. So, where A and B refers to the number of atoms containing pi electrons. And some important classification of cycloaddition reactions are like Diels-Alder reaction, which is also known as 4 plus 2 cycloaddition reaction. And another one is 1,3 dipolar or 3 plus 2 cycloaddition reaction. And another one is 2 plus 2 cycloaddition. So, sir have discussed regarding Diels-Alder reaction and 2 plus 2 cycloaddition reaction in this week 2 lectures. Now coming to Diels-Alder reaction. So, Diels-Alder reaction, it occurs between a conjugated diene and an alkene. So, this alkene is usually known as dienophile. So, this is the conjugated diene and this is the dienophile. So, under heating, it will undergo a concerted process like this. So we can show the mechanism like this. Okay, arrow pushing like this, giving this as the final product. So cyclohexene will be resulted by reaction of this diene and the dienophile. So either way you can show. Either from this side it is attacking, arrows are moving in this direction, or from this side it is attacking and arrows are moving in this direction. Either way you can show. And it was Otto Diels and his research student Diels-Alder uh, who discovered this reaction in 1928, and they were awarded the Nobel Prize for this inventory. So they were awarded the Nobel Prize in 1950 for their discovery of this Diels-Alder reaction. So here in the Diels-Alder reaction, see, this is the diene and this is the dienophile. So orbitals have so the HOMO and LUMO should be in such a way that the constructive overlap will be taking place. So here these orbitals are having same type of like lobes, so they will overlap giving new bond. So here a new sigma bond is forming, here also a new sigma bond is forming, and these two lobes are having a stereochemistry such that a new pi bond formation could be resulted. Okay, so this is how Diels-Alder reaction is taking place. So the black p orbitals are perfectly aligned to make a new sigma bond, as are the two green orbitals, while the two brown orbitals are exactly right for the new pi bond at the back of the ring. So this is exactly what is happening behind the Diels-Alder reaction. So this is a one-step reaction, or it is a concerted reaction which is not going through any intermediates. And for the requirements for the diene. So the diene component of the Diels-Alder reaction, it can be either open chain or cyclic. So cyclic dienes that are permanently in the S-cis conformation are exceptionally good at Diels-Alder reaction. So this is an important point. Diene should have an S-cis conformation for the Diels-Alder reaction to take place. Once it is permanently in S-trans conformation, then Diels-Alder reaction will be not possible. Okay. So cyclic dienes that are permanently in the S-trans conformation and cannot adopt the S-cis conformation will not undergo the Diels-Alder reaction at all. So here you can see this is 1,3-butadiene. So it is an S-trans conformation, but it can, once this bond will rotate, it can convert into S-cis conformation. Then once it is in S-cis conformation, then it can undergo Diels-Alder reaction with this dienophile, resulting in the formation of the cyclohexene. Okay, so here the S-trans conformation is the most favored conformation, but it is not favorable for the Diels-Alder reaction to take place. And also here this S-cis conformation is not much favored, but once it is forming, it can undergo the Diels-Alder reaction. As you can see in this reversible arrow, here this reaction, backward reaction is more favored, as this is the most stable conformation. And some dienes which are permanently in the S-cis conformation, which are good for Diels-Alder reaction, are like cyclopentadiene, furan, and exomethylene diene, cyclohexa 1,3 diene. These all are some good diene that can be used for Diels-Alder reaction to take place. And the dienes which are permanently in the S-trans conformation, they cannot undergo Diels-Alder reaction. So see this one, here it is in S-trans conformation and it cannot be converted into S-cis conformation in any way. So because of that, this diene will not undergo any Diels-Alder reaction. Similarly, this one also, it cannot attain S-cis conformation. Because of that, it cannot undergo Diels-Alder reaction. Now coming to requirements of the dienophile. So they have an electron withdrawing group conjugated to the alkene. So for normal Diels-Alder reactions, the diene will be electron rich and the dienophile should be electron deficient. So we will be considering the HOMO of the diene and the LUMO of the dienophile while we will be dealing with FMO. So for normal Diels-Alder reaction to take place, uh, the,
Hello, the slide is it
hello,
is not showing actually.
what happened?
The slide is not visible.
Okay, let me reshare once again. Is it the case with everyone? Hello, is it visible now?
Yes, it is visible.
Okay. So for the normal electron demand Diels-Alder reaction to take place, so the requirements for the diene is the presence of an electron withdrawing group that is conjugated to the alkene, making the dienophile more electron deficient. So there must be some extra conjugation, at least a phenyl group or a chlorine atom, or the cycloaddition does not occur.
Hello, hello.
Hello, any doubts?
No, no, madam.
Okay, visible now slides. So there should be some extra conjugation, the presence of some phenyl group or a chlorine atom. Otherwise, the cycloaddition reaction will not take place. Uh, normal ethene and all will not easily undergo Diels-Alder reaction. As you can see here, the reaction is very poor. So this is another example, where the cyclopentadiene is acting as both the diene and the dienophile, resulting in the formation of this product. So here, this part is acting as the diene and this part is acting as the dienophile, and it will be giving this final product. Okay. So diene having,
जी अटेंड करायला लागणार आहे मग.
hello,
हॅलो.
hello, any doubts?
हो यस. अरे मी कुठं काय केलंय? काय काय मी काय केलं? तुझ्या हातात तर गेलंय. जॉईन कर लवकर मॅडम काय म्हणते.
Please mute the volume now.
Okay. So for the diene, the requirement is it should have an the diene should have an SS conformation for the Diels-Alder reaction to take place, and for the dienophile, it should be having some extra conjugation, that is the presence of some electron withdrawing group or something that will make it more electron deficient for the reaction to take place in facile manner. So these are some of the examples of dienophiles. Sorry, some background noises coming, that you please ignore. So this is as they have mentioned, the presence of some phenyl group and some electron withdrawing group like the sulfonyl, cyano, and some ester. These are making the dienophile more electron deficient, so that the reaction will take place in a facile manner. So and the features of the products, if we are coming, these three features mean that the compound is a possible Diels-Alder product. So it should be a six-membered ring, because 4 plus 2 cycloaddition is taking place. It will give a six-membered ring, and the presence of a double bond inside the ring. So as you can see, if it is reacting in this fashion, so one double bond will be there inside the ring. So the conjugating group outside the ring and on the opposite side of the ring from the alkene. as we have told, the dienophile will be having a conjugated group, so it will be present outside the ring, uh, which will be opposite to that of the alkene, opposite to this alkene. Okay.
Ma'am, can you explain third point once more?
Yeah. This conjugating group will be present outside of the ring, and it should be opposite, like opposite side to that of this alkene.
Okay, okay, okay. Got it, got it. I think they are talking about the stereochemistry or somewhat, but it's just simple.
No,
Okay.
no, this is just symbol part only. So simplest way to find the starting material is to carry out disconnection, as you can carry out in this fashion. So say similar way we have carried out electron pushing, we do it in the opposite way for the retro Diels-Alder reaction to take place. So it will give these as the starting materials. Okay, we push the arrows in this fashion, we will be getting this dienophile and these diene, which will be the possible starting materials for the reaction. Now we will be discussing few questions based on Diels-Alder reactions. So this is the first question, which is based on some alene. So the major product formed in the following reaction is. So this is based on a 2 plus 2 cycloaddition reaction. Please try to work it out.
Is it 3?
Answer will be actually 2, because this attack will be taking place from the less hindered alkene of the allene. So
Okay, okay, okay.
the given allene system will show 2 plus 2 cycloaddition with another alkene system on the thermal assistance. So the less hindered double bond of allene will participate more in the reaction, and it will give the major product. Other product is also possible, but it will be minor. Since the reaction follow concerted mechanism, stereochemistry of the substituent is not affected. So this is trans. So in product also it will be coming as trans. So therefore the major product will have same orientation as in reactant, that is the product will be trans for the given reaction. So it is a 2 plus 2 2 plus 2 cycloaddition reaction. And here the major point that you have to keep in mind is the less hindered double bond of the allene, it is participating more in the reaction. And since this is a trans alkene, the stereochemistry is maintained as such in the product because it is a concerted reaction. Okay.
Ma'am, in this case, there is not any factor like electronic effect, just as in ketene 2 plus 2 cycloaddition.
Mm-hmm.
I am just asking ki, there we were taking the double bond downside, means we were taking something like electronic effect into the factor.
Yeah, here
Uh,
nothing like that is there.
Here it is just a steric effect.
Yes, yes.
Okay, ma'am.
So here the correct answer will be option 2. Now coming to the next question. Which of the addex A to D is the main product of the following Diels-Alder reaction?
It should be B,
Yeah,
as it is, and simple.
yes. Because here you can see this is also E, this is also E. So that will be maintaining its stereochemistry in the product. And since here it is trans, in product also it will be trans. So this will be the final answer. Okay, like normal. As mechanism, if you want to show, you can show like this, and this will be the product. So we have to see both the starting material and the both starting materials, how the stereochemistry is coming in the starting materials, that will be maintained in the product as well. Okay, so the answer is option B. Any doubts?
No, ma'am, it's fine.
Okay, now coming to the next question. Which of the following dienes cannot undergo Diels-Alder reaction?
Option D can't go because it is in a permanent S transform.
Yeah, so this is excuse me. So this is the right answer. What is it? In all these cases, it can this bonds can rotate and it can result in the SS conformation. But in this case, this is a cyclic system, so this rotation will be not that feasible. Because of that, D will not undergo any Diels-Alder reaction. Excuse me for that noise. I cannot do anything. So option D is the right answer here. So here what we have to consider is the requirement of the diene, that is the permanent SS conformation, or SS like a chance to take the SS conformation should be there for the Diels-Alder reaction to take place. If it is permanently in S trans conformation, then Diels-Alder reaction will not be feasible in that system. Okay. Now coming to the next question. The major product formed in the following reaction is,
Endoduct will be forming. Option C, most probably.
yeah. So here this is a cis-alkene. So it will maintain that stereochemistry in the product as well. So the reaction will be taking place in this manner. Sorry, some problem with my pen. So the reaction will be taking place in this fashion. And this group will be going above the plane, and as per the endo rule, Alder's endo rule. Because of the secondary orbital interactions, the CO2 CH3 will be coming below the plane. Okay, so option C will be the right answer. Something is happening with this pen, sorry.
Ma'am, it's fine. We got the point that it's due to Indo rule. It's
Okay,
forming
okay,
secondary orbital interaction, stabilizing the transition state.
okay, okay. Actually, my net is down. That is why I guess it is not working properly.
Maybe.
Hmm. So the reaction you can show in this fashion, and because of endo rule, these two CO2 CH3 will be coming below the plane. So C will be the right answer. Now coming to next question. Among the following, the number of compounds which can participate as diene component in a Diels-Alder reaction is?
Except 6 and 7, I think all can participate.
This and this cannot
S
participate
is
because of
confirmation.
the strands conformation. All others are having SS conformation, so it can undergo Diels-Alder reaction. So the answer is 6. 6 among this 8 dienes can undergo Diels-Alder reaction. Okay, now?
Hmm.
Now coming to the next question. The reactivity of the compounds 1 to 4 with malic anhydride 5 follows the order.
First will be maximum, second will be minimum.
Yeah, because this to isomerize, then the CH3 groups will be coming close to each other, like tertiary butyl groups will be coming close to each other, so that will be little difficult. So the option were
B
first,
should be.
first is coming maximum will be this one, first one, then this one, then fourth one, and then least one will be 2. Okay, na?
Hmm.
So answer will be B. Next question is, which of the addex A to D is the main kinetic product of the following Diels-Alder reaction?
It will be C most probably. One to adduct and outward group and electron withdrawing group should be cis position. Indo effect.
Mm-hmm. Yeah, this is electron releasing group. So this will be the most electron rich sender, and since it is electron withdrawing group, this will be the most electron deficient sender. So the electron rich sender will be attacking on the electron deficient sender and normal other arrow pushing. So we will be getting CO2 Me and OPH means ortho to each other. And when coming to stereochemistry, CO2 Me stereochemistry should be alpha position.
Same as
uh,
same as that of OPH.
OPH,
Relative stereochemistry should be same.
because of the endo effect.
Secondary orbital interaction.
Yeah, endo rule. Secondary orbital interaction should be taking place. So because of that, option C will be the right answer. These both should be coming in the same direction. Okay, na?
Yes.
So option C will be the right answer. Now coming to the next question. The structures of the major products X and Y in the following reaction are.
Something between C, मतलब third and fourth. Let's check Y.
Okay, I think that reaction you have not clearly studied. Paterno-Bucchi reaction that we will be studying in
Okay.
biochemistry part. So
Okay. Okay.
first, this is the diene. This is the diene of pile, and following endo rule of Diels-Alder reaction, the this COMe group will be coming endo position to that of the diene. So we will be getting X as this product. Okay, it should be coming below the plane, and then
Third and fourth.
Paterno-Bucchi reaction will be taking place by generation of the radical.
Okay. Alkene plus carbonyl compound.
Yeah, yeah,
2 plus 2 cycloaddition type.
yeah.
Hmm.
So we will be getting this as the final product. So option 3 will be the right answer. Clear?
Yes, ma'am.
Okay. I think this is what all I have for today. So we were discussing some of the previous assignment questions from week 1, followed by we had a brief discussion regarding the topic that was covered in this week, and now we have discussed a few examples of Diels-Alder reaction and one example for 2 plus 2 cycloaddition. So you are having any more doubts?
Uh, can you please give some hints on assignment 2, problem 4 and problem 3 and 4?
Problem 3 and 4. Okay, let me see.
Yeah.
Just loading, please wait. Comment the feasibility of the following reactions to occur in a concerted manner through a pericyclic pathway. If they are feasible, write the mechanism of the reaction. If they are not feasible, state the reason for it.
This I think he sir has discussed in the one of the video lectures. This question. It's there in the video lecture most probably.
Both problems.
I think third A is sure. And
Third B, actually the main problem is third B.
third B, it's not in, I think, sir's
Similar
lectures.
type of question like we have seen now.
Yeah,
Uh,
similar.
we have discussed in last week also. I think you have shown. that we have discussed in the beginning of today's lecture. So first, this tosyl group will be leaving, leading to
Hmm.
formation of cyclopropyl carbocation,
Hmm.
and
Yeah.
then ring opening will be taking place in 4n plus 2, that is 2 electron system, 4n plus 2 disrotatory. Then this acetic acid attack will be taking place on the carbocation, right? So you have to see if after pushing the electrons will it be feasible or not. And the other question you can see, like its thermal condition, under thermal condition if it is feasible or not. Otherwise, if it is not feasible, then you can draw and show photochemical condition also if it is giving the products. Okay.
Okay, okay.
Other questions are okay now. Some concepts of this week 2 assignments are coming from week 1 also.
Yes, ma'am.
Like last question is coming from Nassarov cyclization, which we have discussed. One question we have discussed last week based on Nassarov cyclization, but few questions only this time.
Hmm.
Any more doubts?
Ma'am, the problem which I have,
Okay, okay. That I will show once again.
you have discussed in it in beginning of the session.
Huh.
Oh, okay. I will see it in the
It's
YouTube.
okay. It's okay. We have time. We can discuss.
I just got slept.
It's okay.
Means-
It's okay. Actually, now here we can explain it based on the living group ability of bromine. But when we will come to this question, it will be problematic, right?
Yes, ma'am.
Actually, uh, we have seen it is a two electron system, that is 4n plus 2, where n equal to 0. So
Yes.
4n plus 2 delta, it is disrotatory.
Hmm.
So we have to, so this is the bond, that is if we are considering Cl and bromide. If we are considering, this is the bond that is going to break. So this is the orbitals that are overlapped. So it will be opening in this fashion, like this. So the orbitals will be like this after opening, right? So it is orbital concept that we have to take into consideration. So this Cl, whose antibonding orbital is here, so this bond which have opened, it can donate its electron to this antibonding orbital, making this Cl bond weak, and hence the Cl is leaving here.
Okay.
So that is why in this case the uh, Cl is leaving instead of bromine. But here the donation is taking place to antibonding orbital of bromine. So whichever group is coming in endo position to that of the bond that is opening, that group will be leaving.
Ma'am, you have marked third as the right also, right answer.
Sorry, disrotatory. Sorry, four I have marked. B is formed as the major product via disrotatory ring opening.
Okay.
Fourth one.
Uh, I have understood it in a completely different manner.
Hmm.
I have to show the slides to
Okay.
explain what I
You can show. I am
uh,
sharing my screen.
don't even. Okay, here it is. अरे इसमें नहीं होगा.
Hmm?
It will take some time.
Okay, okay. No problem. What happened?
Actually, I am not that file in my laptop, so I have to just share it on laptop and then I have to show you.
Okay.
It will just take a minute. Let
Sure,
me
sure.
show it fast.
No problem. I can wait.
Can you open my assignment? Means it's permission to open or means like
Hmm?
okay. Let me just show you.
Okay.
I think it's visible.
Yeah, it's visible.
Okay. Uh, can you see this one?
Yeah.
Uh, Here the transition state that I have drawn.
Hmm.
In this one, both see both hydrogen and OTS
Hmm.
both are on the same side. Means the hydrogen which are presented junction position
Hmm.
and OTS the living group
Hmm.
all three are at cis position.
Hmm.
So after that, when we are doing this rotation, then it is like forming trans double bond inside a seven-member ring.
Hmm.
So we were saying this is not feasible one.
Hmm.
But while in this case, both hydrogen which are present at junction and leaving group,
Hmm.
they are means hydrogen at junction and OTS,
Hmm.
they are uh, relatively trans. And in this case, product was forming means cis double bond was forming inside the six-member ring, which is a stable one.
Hmm.
So
That
this was
only.
the concept.
This rotation, there are two possibilities now. Either we can open it, either both bonds can open outwards or both can go inwards
Okay.
in this rotation. So whichever is giving like cis conformation, that will be feasible. And in that case, um, the bond which is breaking now, its slope will be coming periplanar to the antibonding orbital of the leaving group. So in that case, leaving group can leave very in facile manner. So when in whichever case the bromine and chlorine are leaving now, you are showing two different examples. So in that cases, the bond
Hmm.
will be opening in such a fashion that we will be getting the said conformation, said alkene. And
Okay.
uh, so the like the antibonding orbital of whichever halogen is coming in periplanar fashion to that of the bond that is opened, that will be getting the electron density from that bond. And that will be and like if we are filling electrons in the antibonding orbital, then the bond will become labile and it will be leaving. That is what is happening.
Okay. Okay. Okay, ma'am.
Hmm. So no other doubts, right?
No, ma'am, it's fine.
Hmm. So thank you.
Thank you, ma'am.
Hmm.